Welcome to the Stat AI podcast.
Welcome to the future of emergency medicine, a realm where artificial intelligence isn't just a buzzword, but a beacon of hope and a tool for transformation. I'm DJ Apakama. My co-host Ethan Abbott and I are both emergency physicians, and we have witnessed firsthand the burgeoning role of AI in our field. Our everyday experience grappling with healthcare disparities and social challenges have led us to a pivotal question. In the wave of AI applications, what changes are coming to emergency medicine, and will they be for the better? This podcast was born not just to ask these critical questions, but to seek out answers from the experts, to understand and to demystify the potential of AI in emergency medicine. We believe in bringing this conversation to the wider community to embrace AI as a tool for positive change. This podcast is our exploration of that future, a journey we invite you to join. So let's embark on this path together to learn, to question, and to envision a new era of emergency medicine enhanced by the power of AI.
On this episode of the Stat AI podcast,
it is incredible that we've been asking humans for so long to take millions of pieces of medical data, both from the literature and from the patient, synthesize those and come up with what should happen at this point in time, right?
Our goal is not just to throw computer science at a problem, or to figure out how to use computer science and math to take the type of things that cabs and other doctors do in their day-to-day and turn it into something we can scale up through our computer systems.
In my opinion, AI has it's going to have a transformative role in education. It could have a really positive transformative role, or it could have a really negative transformative role. It's the way we apply it, both as learners and as educators.
Hey, DJ, what's going on today?
Hey, Ethan. Today we're discussing a fascinating development in AI, DeepSeek R1, which is a new large language model designed to improve reasoning ability using reinforcement learning instead of traditional supervised fine-tuning. And that's a lot of words. Don't worry about it. We'll break it down. But this is a big deal because it challenges some of the assumptions about how we train AI to think. So we'll start with a fundamental question. What is reasoning in artificial intelligence, and why does it matter?
I think when we talk about reasoning in AI, we're referring to a model's ability to logically process information, solve complex problems, and make inferences beyond simple pattern recognition. So in the context of this DeepSeek conversation we're having, most AI models, including the ones we use in medicine, really excel at pattern recognition. They tend to identify trends in massive data sets and use those patterns to generate responses. But true reasoning, which is the process that we as physicians use every day, goes a significant step further. It requires an organized thought process and the ability to break down problems into steps and self-correct and even verify one's own work. So for example, let's say you're in the ER and a patient presents with abdominal pain. Pattern recognition might help you recall similar cases and suggest a possible diagnosis such as appendicitis, diverticulitis, pancreatitis, but reasoning allows you to consider atypical presentations, which is significant for emergency medicine, conflicting lab results, patient history, adjusting your differential as you gather new pieces of data. This is exactly what the DeepSeek R1 model that just recently came out is trying to improve, is giving AI a structured way to reason through problems instead of just regurgitating information.
Right. And that brings us to the unique approach that DeepSeek R1 took, which was that most AI models are trained using supervised fine-tuning. So that was one of those words I said we'd come back to, which essentially means that they're learning from massive amounts of labeled data. They are memorizing what human beings told them is correct. They are not applying their own judgment. So DeepSeek R1 is challenging that by relying primarily on reinforcement learning. We're going to need to break this down because I think reinforcement learning is a concept that's less familiar to most people than supervised learning.
Supervised learning is when we give the model like thousands or even millions of examples of a task, and it starts to learn by copying what it sees. So in the context of medicine, for example, if we train an AI model to read EKGs, we would feed it labeled data and say, this is atrial fibrillation, this is ventricular tachycardia, this is an ST elevation MI, and the model learns to recognize those patterns. With reinforcement learning, the AI learns by trial and error, receiving rewards for correct answers and penalties for incorrect ones, just like how we train a medical student to think through a case rather than just memorizing textbook definitions.
What are the penalties for medical students?
Many, many penalties.
Sorry, continue.
As we know from being medical students, there are many penalties. Yeah. So I want you to imagine a resident in their first week of training. At first, they make mistakes, but through feedback from attendings, patient outcomes, and clinical experiences, they refine that reasoning. That's kind of how reinforcement learning works. The AI isn't just copying answers. It's figuring out what works through self-correction and adaptive learning. DeepSeek R10, which was the first iteration of this DeepSeek model, was trained entirely using reinforcement learning without any supervised fine-tuning of the model. And this was a bold experiment because no major model had attempted this before. The results were impressive, also problematic.
As are most things with AI, let's talk about the pros and cons of this approach. So DeepSeek R10 developed strong reasoning behaviors naturally, and that's important. It improved itself by optimizing for the best possible answers, but it also suffers from readability issues. It was great at solving problems, but the responses were messy, sometimes mixing multiple languages and hard to understand. This model is not optimizing itself to be read by humans when it's just working on itself internally. So even though we're saying that it's mixing multiple language, it's very hard for humans to read, but rest assured the model is understanding because it is actually making improvements. The researchers wanted to counteract this issue and developed DeepSeek R1, which introduced a cold start phase before reinforcement learning. They first trained the model on a smaller, curated data set to give it a good foundation for communication, and then applied reinforcement learning to develop its reasoning ability. Basically, they taught it how to communicate with humans before they taught it how to reason. And the result was that DeepSeek R1 now matches or even outperforms OpenAI's top model. Like, this is OpenAI model that at the time, OpenAI has since responded in a big way, and maybe we'll talk about that next month. But at the time DeepSeek R1 was released, it matched and even outperformed OpenAI's top model at that time, O1 Pro, in math, coding, and problem-solving tasks. So let's break that down. What are these benchmarks actually measuring?
Usually evaluated using standardized benchmarks, which assess different skills. DeepSeek was tested on several major ones, which included it in 2024, which is a math reasoning test where it had about 79.8% accuracy, which was similar to what OpenAI had demonstrated. The Math 500, which is a complex math reasoning test with a 97.3% pass rate, making it one of the best AI models for math, actually. And then Code Forces, which is a coding challenging benchmark, and achieved 96.3% percentile, outperforming most human coders on that, as well as the MMLU, which is a general knowledge test, which had 90.8% accuracy, slightly below OpenAI's benchmark, but significantly better than previous open source models. So these results really show that DeepSeek is an exceptionally strong, structured, logic-based model, really achieves significant performance where most AI models struggle. But here's the real game changer and what we want to talk about. The research team at DeepSeek distilled DeepSeek R1 into a smaller and more efficient model, which I think is a significant achievement.
Right. The distillation is a huge deal because one of the biggest problems with AI models is that they are too large and expensive to run efficiently. No one can just create another ChatGPT because the upfront costs of ChatGPT at this point is billions of dollars. So you really have to be a well-resourced or moneyed operation to even start of thinking of creating these large language models. But DeepSeek's R1 researchers took the reasoning capabilities of their large model and then compressed them into a smaller model, as small as 14 billion parameters. So very huge compressions, but they were able to maintain that strong performance. So this would make AI more accessible, cheaper to run, and easier to integrate into real-world applications, which is especially important in medicine. If we want AI tools in the ED, we can't afford to run massive resource-intensive models for every case. It's just not going to work.
The real question is, what does that mean for medical AI moving forward? And I think there's really three main points. One is AI models will really, I think, no longer need mass amounts of labeled data. This reinforcement learning could allow them to learn through self-improvement, just like humans. The second point is smaller AI models can inherit complex reasoning skills, making them more practical for clinical settings in hospitals. The third major point is reinforcement learning could be used in clinical AI to enhance decision support tools, potentially improving diagnostic accuracy without rigid rule-based programming.
Right. And so those would be all of the benefits. But again, we said there are some drawbacks. There are still challenges. Reinforcement learning is difficult to control. Early versions of DeepSeek exhibited reward hacking, where the model would take shortcuts to maximize rewards without truly reasoning through the problems. There was actually a story the other day about how GPT and other models would use evasive tactics when they were told they were going to be playing the best chess model in the world in a game of chess. In order to not lose, GPT and other models would just hack into the root file of the game and say that they won, making the other model automatically forfeit. And this behavior was actually exhibited quite frequently across models and some times without even prompting. So this reward, or that the desire to achieve a goal is very strong in AI. And if it's going to take shortcuts just to achieve a goal, that's really what we call sycophancy, where they're starting to just really want to please the user they are working with. While RL models are great at reasoning, they're still limited by the quality of the feedback they receive. Just like a resident who learns the wrong lesson from a not great attending, AI models can also reinforce flawed reasoning if not trained carefully and accurately.
Where do we go from here? The next big frontier, at least in my mind, is combining reinforcement learning with human oversight, where these AI models can learn independently, but are periodically corrected or verified by expert clinicians. This could lead AI to not only assist physicians, but actually improve its own diagnostic skills over time, which would be representative of a true learning assistant rather than just a static tool at the bedside.
Yeah. And so I think this is one of the most exciting areas of AI development, and it's going to shape how we interact with AI in medicine for years to come. DeepSeek R1 is proving that reasoning in AI isn't just theoretical, it's happening right now. So the big question is, how do we responsibly integrate this into clinical practice? And I think we have some amazing guests today to help us answer that question. Today we have Dr. Travis Zack, who is an assistant professor in the Helen Diller Family Comprehensive Cancer Center at UCSF. He studied physics and biology at UC Berkeley, completed his PhD in biophysics at Harvard, and earned his medical degree from the Health Sciences and Technology program of MIT and Harvard. His clinical focus is pancreatic oncology, and he leads a lab focused on descriptive and predictive model development for applications in electronic medical data. He serves as a consultant and lead physician for OpenEvidence, bringing his clinical expertise to shape how the platform answers medical questions in an expanding information landscape.
All right. I'm excited to introduce Varun Mangalick. He is a software engineer working at OpenEvidence. He studied math and computer science at MIT and has worked at several startups in the health and biotech space. Welcome, both of you, to the Stat AI podcast. Super happy to have you here.
The overlap of MIT being very strongly represented today. So I guess we can ask both of you, but I'll start with you, Dr. Zack. How has your background in physics and biophysics influenced your approach to predictive modeling in oncology?
Very much at a non-traditional trajectory. I still feel like every step of the way I learned something helpful. Physics is such a great fundamental background to understand how to ask and answer questions. It's great for problem solving, no matter what you end up doing. I picked it because I loved doing it. It was a fun set of courses. Was mostly interested in just imaging research at that point, single molecule imaging research. Got interested in cancer research during graduate school with family members with cancer, and finally progressed to going back to medical school. During graduate school, my degree was in biophysics. I did mostly algorithm development in cancer genetics with the big data sets at the Broad when we were doing a lot of bulk sequencing. In third year medical school, one thing that struck me is how much data we're asked to process as clinicians. We do have a lot of data, but when we're on rounds, we're supposed to determine whether a change of 0.5 hemoglobin over 2 days really represents a significant difference or marginal error, an error. And 100 things like that every day. And we're making real decisions for patients on that. And those kind of realizations made me switch from mostly a genomics focused at medical records. I think the backgrounds for signal to noise and pulling out longitudinal data a lot of the things translated well regarding both my undergraduate work and my graduate. But as someone else mentioned, a lot of stuff was self-taught these days. Everything changes so quickly. You can't assume that what you learned in undergrad, graduate school, or medical school for that matter is the foundation of knowledge that you're going to build on. I learned a lot of it myself as I was doing more research, and I continue to do that. Every time something new comes up, I'm like, okay, how do I create a research problem where I learn on that?
That's an amazing way to approach learning, like research through learning. I agree. So I guess we can ask Varun the same question. How does your math and computer science inform your approach to healthcare challenges?
I've always been super interested in the bio and health space, even before college. In my approach to solving problems, I liked taking things from more of like a math and computer science perspective, which is a very like analytical, systematic way of addressing things. And so when I went to college, I felt like studying computer science and math would give me the best tool set to solve whatever problems I want in the future. Eventually, I ended up working at a couple different biotech startups, one in the cancer drug discovery space and one in the metabolomic space. And I think when I was coming to OpenEvidence, I felt like it was a really cool opportunity to apply this new technology, which is large language models. It was a really cool way to use my computer science and math training to solve problems that felt like they were actually impacting such an important field like health.
That's awesome. I want to pivot back to Dr. Zack. Tell us a little about your early experiences at OpenEvidence as a clinician and what initially drew you into the fold of being a team consultant there.
I was collaborating with a graduate student in one of the oldest AI and medicine labs at MIT, one of the grandfathers of the field. We were doing a project. We were doing a couple of projects. One was on diagnostic reasoning back before it was cool. The other more recently was on bias in language models as it relates to medicine. And so he, while working on that, and after he graduated, joined OpenEvidence really at the very beginning. I started as one of the head ML engineers from MIT. We had a good relationship, and a lot of that relationship was him asking me medical questions as it related to his work, because I love talking to him. He's a really smart guy, and he told me about OpenEvidence. He told me the goals. I have been fascinated about this topic for a long time. I did an NLP project on it before we had all the tools we had now on how to collect that information. And it's this multivariate optimization problem that I think is incredibly difficult and important. He showed me mocks, how it was working. Most of my responses were, this was pretty terrible, but I get where you're coming from.
Yeah.
Eventually I was like, we're talking a lot, and they're like, we'll have you on as a medical consultant. That's where it came from. For me, I could see that this is something that was just incredibly necessary, and if done right, could really transform how I practice. So I was an early bandwagon adopter, I guess, is how that relationship.
Following on the heels of that, Varun, maybe you could answer a question, what are how's your approach to the technical challenges of combining these different types of medical data? How are you going through the data? How are you organizing it so that it makes sense to you and is readily accessible to the models, to your MDs, to Travis? How are we doing?
We are trying to make this useful in a medical context, right? If you just take like 10 computer scientists, throw them in a room and say, solve medicine, no one's going to actually make something that's useful to a medical professional. One thing that we really try to focus on when we work on these things is we have people like Travis or other medical advisors that we can consult to say, okay, if you're looking through these types of problems, if you're trying to find relevant parts of medical literature, how would you search these things out? How would you pick what's relevant? How would you decide what to use to actually figure out what to do in a given scenario? Our goal is not just to throw computer science at a problem, but to figure out how to use computer science and math to take the type of things that Travis and other doctors do in their day-to-day and turn it into something we can scale up through our computer systems. A lot of this comes down to how you bridge the gap between what a computer can do and what Travis's brain can do.
How far along it? No, I'm joking.
I word out, we have a ways to go, but every day I'm like, oh, it's great that I'm working to put myself out of business.
Right. It does sometimes feel that way. And I feel like people may feel that that's kind of a hyperbolic statement, but in some ways, these models, just what they've been able to accomplish in the last, let's say, 18 months, it's really been from a place where I'd had no concern whatsoever to I can now envision it. It will probably happen at some point in the future.
I've been a glass half full person, but I've almost converted a little bit to the other side. It is incredible that we've been asking humans for so long to take millions of pieces of medical data, both from the literature and from the patient, synthesize those and come up with what should happen at this point in time, right? Not that a computer can do that yet, but it's crazy that we've been thinking that humans can do this because this does a lot to process.
That kind of brings me to a paper that was published, I think, last year. I'm sure you were working on it well before then, but wanted to kind of get your thoughts on it. The title of the paper is Assessing Large Language Models for Oncology Data Inference from Radiology Reports. And so I'll just give a quick explanation of the paper, which essentially was looking at proprietary and open source large language models to compare the detection of disease presence, location, and treatment response in pancreatic cancer from radiology reports. You were able to find that LLMs, especially GPT, are proficient in deriving oncologic insights from radiology reports, and at varying degrees of success, every other model was able to do it to some degree. I think, to me, when I read this, one of the things that comes to my mind, especially with recent developments, specifically the DeepSeek development, is that potentially we've been talking about zero shots and ways to use these models in their base format. There's been a new paradigm with these models now exercising chain of thought and reasoning, and we're now seeing that in the open source arena. And so I guess my question is, do you think that in environments where proprietary models may not be successful, we will see open source models take the lead and do things that may not have been possible before?
So a lot of questions there. First of all, so that project was actually, a graduate student during her rotation. So Dr. Li Ching Chen, or doctoral candidate Li Ching Chen, and she was amazing. She did it all. But during that process, right, where she was doing it, I text her like every 2 weeks. I'll be like, oh, new model came out. You got to use it. You got to do this one too. And that's the pace. New models are breaking the benchmarks all the time. I'm sure both of you are experiencing this in the research realm, how rapidly this kind of stuff becomes boring. Like prior to GPT 3.5, that project would have required like a year and a half of work, of annotation, of fine tuning a model. And chances are it'd be like half as good, right? That would have been pretty significant, right? Like to get something that is a multi-class classifier of some complex inference in a radiology is pretty significant. By the time we published it, this is almost just like a stepping stone paper, right? Like, yes, of course it does extraction. Why would it do extraction, right? What are you going to do with that? That's all. I think the research has moved beyond extraction in a lot of ways. Yeah. Clearly, we're not 100%. We're doing a lot of work to get to 100%, both in proprietary models and open models. Now we're at the point where, so what? You're doing extraction. What are you going to do with that information, right? Which is a great place to be if you're in the research space, because you have this entire realm of the dark matter of medicine, which is the clinical node, that is now open to you. And now you have to think about, what do you do with that information? Which is fun, but it's a mind shift for sure. For people who, a lot of it is just like, how do we get the information, right? In terms of getting the information, you mentioned 2 points to talk about. Proprietary means when you're using the model, it means a few things, but in practical terms, when it comes to medical use of LLM, means you are sending your data to somebody else. They are processing it and then sending it back to you. Most clinicians, when they hear that, a lot of red flags are going to go off, right? We have do no harm is our number one priority. And then we have a bunch of legal reasons not to do that on top of that, right? So sending your patient's data to an outside system comes with a lot of information security challenges, privacy challenges that you have to be very careful. Now, a lot of systems have done it. For example, UCSF, we have an Azure HIPAA compliant platform that allows us to do that. We work with de-identified data for extra protection, et cetera. Most places don't have that. So that's one problem with proprietary systems. Open systems are this idea that if you have the right computer environment, you can take everything inside your firewall. And when you send your data to that, nothing leaks. So at least from a lot of security and privacy standpoint, it's a better way to do things. Many people listening probably already understand those distinctions, but I think it's important to discuss. Why do we care, right? There is a lot of promise in open model. What we thought a year ago still holds true, which is open models are very powerful. They're often about 6 to 9 months behind, which I think a lot of people think that DeepSeek is probably around there. People think it's great, but I think and like Varun maybe could think about it a little more. It's probably not quite as good, right? What are the trade-offs? Does the fact that it's open, that allows you to bring inside your firewall and use it on your data and make sure it doesn't leave, that you can modify it, that you can make it better in an easy way without charging a bunch of money? Are those things worthwhile given the trade-offs that maybe it's not quite as good? That's every day we talk about that in lab. Like we have both models we can play with. This is all research stuff, open evidence stuff. Those are my thoughts. Yes, open models are very good. Open models, incredible compared to what we were thinking a year and a half ago. Any model could. I would still say proprietary models, state of the art most of the time. So if you really need the very best, often you have to default to that. But I think most of what we're doing in the lab is how do we take things that we can get from a proprietary model, which would cost us literally hundreds and thousands of dollars to do on all of our patients, learn what it understands, which is called distillation, and then train an open model from that information, from what it's learned, so that we don't have to pay $100,000. We pay hundreds of dollars and have something that works here. I don't know. But from a research perspective, that's the things I think about proprietary versus open.
Yeah, Varun, what are your thoughts in that same vein, thinking about proprietary versus sort of local models, homegrown models?
Yeah, I think a lot of what Travis said about like the open source versus proprietary ones, totally agree with. I think that generally the proprietary ones tend to be a little bit ahead of the curve. The nice thing about the open source ones is it makes it easier for people to build off them and to treat them almost like a tool as part of a larger product. If you look at models like the DeepSeek's R1, GPT-0, 2, 3, these basically, they take some base model and then they are building upon it to create these like reasoning systems, right? And I think that this really represents a shift from just this base language model to almost like a complex system or product that is doing something with those base models as a building block to it, right? And so I think that no matter what, when you're taking these base models, whether they're open source models or proprietary models, a lot of the benefit in a system is what you build it to be good at. Even if you look at DeepSeek, if you look at the metrics that they reported, it's mostly good at math and computer science competitions because those are really easy things to generate evaluation for. It's very easy to say, okay, I'm going to generate 1,000,000 math problems because I can probably generate the answers at the same time. Therefore, I'm guessing that model is going to be especially good at those. I think that for whatever systems you build on top of LLMs, they're going to be really good at the things that you focus on making them good at. And I think that it's going to be the case no matter what you use as that building block. Like if your Lego's a proprietary model or an open source model, a lot of that just changes marginal quality differences and the amount you pay. But I think where the big advances are happening and are going to continue to happen is how you build on top of those Legos to make a product that's really aimed towards doing something really well.
Gotcha.
That's great.
Could you walk us through how you might build a system to ensure accuracy and reliability? Obviously, one of the huge things that we're going to need in medicine is both of those things, as close to 100% as we can get them. Hallucinations have been a big conversation around LLM. So how do you mitigate that? Is it through architecture, using essentially a RAG on steroids, bespoke prompting, or really on the training inference side?
I'll jump in just a bit and then break that. So what I would say is those are all really important questions, but there's a more fundamental question that is actually harder for a lot of cases, right? And it was what you said first is how do you ensure accuracy that is like sensitivity and specificity? The first step to that is how do you define sensitivity and specificity in your question? Right? So obviously, statistically, the definitions are easy. I will take the open evidence case, and then maybe I'll take some research cases. The open evidence case is the hardest version of this. So how do you define sensitivity and specificity when you want to get the right answer? It's the right answer with the right citation. It's not enough to just get the right answer. That actually might be easier. The harder thing is to make sure that when I look down at what it's getting, like what that citation is, it's what I expect to see. The reason that's hard is the answer, right? Okay, that's a sensitivity. Specificity is the citation. Both of those are hard from a definitional standpoint. Not only they're hard, they're moving targets. In the case of open evidence, where it's an individual physician may say, you know what, I don't really care what the guideline says. I need the primary New England Journal paper. And the other person is like, I don't really care what the New England Journal says. I want what the society says, right? From that perspective, it can be hard. Building these models for research, it can be hard too. Like you could think about, my favorite example is I'm really interested in using these for the deep kind of dark matter of medicine, which is adverse events and how the patient's actual subjective response to medication. are very hard to pull out prior to these language models. And I think we can get a richer understanding of that by using language models. I have so many cases where the note says both the patient had diarrhea and the patient had no diarrhea, right? I've written those notes. We're all busy. We write those notes. So the hardest thing is determining what is your gold standard? How do you define accuracy in your question? And you mentioned a bunch of different strategies that we can use. I use all of them depending on the question. I think OpenEvidence uses all of them depending on the question. In general, I would say we throw everything you throw at it. The most important thing is taking a scientific approach, which is, this is my metric. This is what I believe is the best way to assess the model I have. And these are the experiments I'm going to do to determine whether I'm hitting that goal and if I'm moving forward towards it. One of the great things about having so many people with a good research background as part of OpenEvidence is watching that process, watching them go through that process of how do we best define that gold standard, even though it is not, it's shifting, right? It's flexible. It's hard to get at, like, what is our gold standard for this?
Sometimes I'll say the gold standard happens to be Travis's brain, but
You'd be surprised how many times in medicine it comes down to expert consensus. So yeah, that's fine too.
I know you'd asked a bunch of questions before. I kind of forgot what some of them were. So would you mind restating?
Sorry.
Just,
this is
I'm
my,
gonna
I
stop
warned you
asking
guys.
compound questions. Just one question here. How are you dealing with hallucinations?
Yeah, absolutely. So you'd mentioned that one possible approach being RAG. As Travis alluded, we tend to use a lot of different techniques to answer different types of questions. In some cases, we do use RAG approaches that are similar to RAG. So I'll give a little bit of background on what that is and how that's beneficial for us. For people who are not familiar, RAG refers to retrieval augmented generation. The idea is, instead of just asking an LLM, what is the best treatment for cancer? An LLM has been trained on anything and everything that whoever made it could access. This could include people talking nonsense on Twitter or Reddit, and you don't necessarily want your question just be answered by those sources, not only because they might not be trustworthy, but the model won't necessarily even know where it got that information from. And so the idea of RAG is, how can we fix that problem? Well, what if we start by figuring out just what information we think is actually reasonable for a model to pick from? And then when someone asks a question, we figure out what the most relevant information is from our corpus. And then we use that to formulate an answer without allowing it to use any information outside of that corpus. So the idea is, you can think of this a little bit more similar to how like something like Google search works. Like if you're looking up stuff on Google, you get a list of links, right? And then if you imagine just taking the best links from there and using those to generate an answer, assuming the links are only reputable sources, that is what this type of system is doing. If your answers are built from reputable sources, in particular like published medical literature, then hallucinations become a lot less of an issue, because hallucinations primarily come from the model just answering based on anything and everything. If your system is saying, let's find the most relevant things among only reputable published literature and only use that to answer a question, then the question is always going to be grounded in reputable medical literature.
There are a lot of sources of error. And the more subspecialized the question, the more sources of error. Hallucination is one source of error. It's something that people have locked onto, I think, because people gave it a really fun name. It comes up with a fun topic. It actually, the term itself gets overused for different types of error. And the term I like more for that specific kind of error is confabulation. These models were trained, which is great for medicine. Like medicine people, I mean, it might have been a while since psychiatry, but the idea of confabulation is it's making up a memory that doesn't exist to please the person in front of them who's looking for that piece of information. And that's what the reasoning model is doing, because it's trained to be a pleaser, right? Like there's this alignment technique that goes through most of these models where they want this piece of information. I don't know where it is, so I'm just going to give them something, right? That is one source of error. I would say that in 2025, because it was such a focus, it is not as big a deal as other sources of error. For OpenEvidence, that is a solved problem, more or less. There were other challenges, right? Mostly related to, how do we synthesize? Okay, we have the right sources of information. How do we make sure we have them, we pull them? And how do we make sure we synthesize them for the question that's being asked? When I say I feel like hallucination is mostly a solved problem, I don't want you to hear we're perfect or language models are perfect. What I want you to hear is there are so many sources of error. hallucinations one, and we focused a lot, we being the community, have focused a lot on bringing that down. Other errors exist. I don't know if you believe that or not, but that's my opinion.
I think I'm going to adopt confabulation from now on. It sounds better. We wanted to pivot to something a little bit different, Dr. Zack. We wanted to see if you could provide any specific examples. This may not reflect current medical practice, but are there any situations where AI-driven insights, other than OpenEvidence or other tools you use, have influenced or impacted clinical decision-making in your day-to-day practice of medicine?
Yeah. So I will do it a few different ways. When I'm in clinic and I have OpenEvidence on a browser, there are a few situations where I find it really helpful. I'm a subspecialist, so I also think about how a generalist might use it. As a subspecialist, I use it in a couple of ways. One is I know what I'm supposed to do, but for specific reasons, I need to know why I'm supposed to. So examples such that, yes, I know that this person's supposed to get this chemotherapy. It's the same one I give for every patient in this situation. They're asking what the overall survival is for them who have positive lymph nodes. I don't remember what that is, right? Like I remember what the trial is potentially, but I don't have it off the top of my head. Normally what I'd have to do is go find the trial, dig into it. Now it's easier for me to pull up that trial because I asked for it and get that information. So being more grounded, not just in what the answer is, which for the things I do every day, I know, but getting better at remembering why. So having a better foundation on the evidence for why I'm doing what I'm doing, which I think is important, but it's important, but also it's really useful. The other one is all the things that come up because we work in a system that is so interconnected, the human body and pathophysiology. When I'm treating a person for pancreas cancer, they may have Parkinson's, ALS, they may have congestive heart failure, right? Any of these other things may come up and I haven't seen them since I was an intern. And I don't know exactly, if there are specific things I need to worry about or ways I have to deal with these comorbidities or externalities to make sure that I'm treating the patient as completely, as opposed to just looking at my disease. So again, as a subspecialist, that's another thing I look at. I assume it's for this therapy. Like, should I be worried about it? Like, give me a synopsis of it, right? So using it for things I don't see every day, right? So that's kind of the two things I use as a specialist. I will also say I tend to use it for active learning outside of those realms when something comes up and I don't need to address it, but it's a lot easier for me to learn about it if I can just type it in and read about it. I was like, I'm not spending 20 minutes learning about this, but if I can spend 10 seconds, I will. So that's how I imagine a lot of subspecialists use it. I would say for generalists, there's the pressure on you, right? Or even if I was a community oncologist, are way higher. When you're a generalist, you have to see 1,000 different things and you can't be ready with what are the 2025 guidelines on those 1,000 different things every day, right? So to stay up to speed with what the evidence-based practice are for each of those things, every time you see that patient, you may have to look this up. Like, okay, now I got to go to the ADA guidelines. Now I got to go to the NCCN. Even if it's bread and butter, because we are learning more and more about every single disease, the specific recommendations for every single one of those scenarios become more fractured and harder for a generalist to understand. And so finding a way to find those easily with current guidelines or current recommendations, if they are not within a guideline, I think is how a lot of generalists, which we've heard has been really phenomenal. Just to make sure that, what I always tell these guys is I want to make very clear what is the alternative to OpenEvidence in a lot of practice. The alternative to OpenEvidence is not, okay, well, I guess I'll go look it up on PubMed for half an hour, come up with the right answer, and then provide it. The practical alternative in a lot of cases is I'm just going to YOLO and I think this is right. This is what I seem to remember and go for it. That's the reality, right? It's like we don't have a half hour for every single thing. And that's unfortunate, but I think that's the reality. That's how I see a lot of people using it. That's the feedback we've got.
Yeah, I think to add to that feedback, Ethan and I use it. We love it. And I think part of the way that I've been able to use it is exactly that second part of questioning why we do some things and pushing the residents. We work clinically with junior doctors, and so they're training, they're learning, and a lot of things are done because of culture. What's really nice is that with OpenEvidence, you can investigate if our culture is consistent with best practices, which hopefully it is most of the time, but it's not always. And then you can talk about why that might be the case. I find it to be extremely helpful.
Thanks for bringing that up. I would like to give a spiel about teaching language models.
We love it.
I was talking about this from the learner perspective, just as someone who's already on faculty or already, an attending level. In my opinion, AI is going to have a transformative role on education. It could have a really positive transformative role, or it could have a really negative transformative role. It's the way we apply it, both as learners and as educators. In my opinion, the way to do it is thinking about it from an active perspective versus a passive perspective. And as long as we think about that, I think it's going to have a really positive role. What I say with an active perspective, I'll tell you what, I'll flip it up. What is a passive perspective, which we have seen? We have seen learners copy paste some huge portion of text and say, can you give me the answer and the references to make it look like I was thinking about it? Like, that is the passive approach, right? And you can see it going very wrong in a lot of people doing it, right? So what is the active approach to learning where you can actually accelerate how much you're learning and your basis for evidence? It involves two steps. One, thinking about the question. Why do I have this question? What are the important pieces of information from my patient that I need to provide to answer this question? So that's an active process. Thinking about your patient, thinking about the answer you want. And then when you get the answer, actively processing that answer, understanding why that answer came about, and being critical about it, right? Does this answer the question of the patient in front of me? Those are actually two different things, right? I asked a question, but I had to simplify it. You can't ask a question about an entire human being. So that kind of active process, now, if you do that, you have internalized so much more than it would take 20 minutes, or longer if you're a trainee to synthesize that much information. I think can accelerate things if you use it in the right way. So that's when I talk to my learners about using things like OpenEvidence, that's the kind of thing I try to impress on them. Please don't copy paste. Please think critically from the input and the output perspective.
Oh, that's great. We actually had a guest on for our last episode and talked a lot about medical education. And that's just a really great way to think of it. Yeah, thank you. I wanted to pivot to a question to Varun, talking more about some of the data engineering that goes into your work. It's a question that DJ and I were thinking about was when you're thinking about integrating AI tools into like clinical workflows, and this extends beyond the user interface, what are some of those key engineering considerations you think about for the typical clinician?
Yeah. So I guess when you're referring to clinical workflows, are you referring to could you clarify that a little bit?
So for example, for OpenEvidence, what are the considerations on how a clinician might use it in terms of both the user interface perspective for easy accessibility and the inputs and outputs and how those can impact, as I'm seeing a patient, kind of what Dr. Zack was describing previously? I don't know if that makes sense.
Yeah. So I think the base form of OpenEvidence that we've implemented here is something where it's super easy to open up this app, ask the question, and get an answer really quick. And I think that we wanted to really focus on making sure that whole experience is as easy, seamless, and convenient as possible, so that it's something you can quickly use in the midst of whatever else you're doing in the clinic. I think when we're thinking about other possible inputs, there's a lot of really cool ideas, for example, about we could integrate this with AI scribes, we could integrate this with EHRs. I think these are all things that we have on our mind as potential future steps with OpenEvidence. But at the end of the day, we just want to make sure that this tool is really good at answering the questions that people have. All these other clinical workflows that we could potentially integrate would just be ways to broaden the number of scenarios where this can be useful, but the tool itself has to be useful for those to be worth it.
And
that's great.
I would say that a lot of what we've already done, they spent a lot of time thinking about how do we create the exact same user interface, but be mindful that there may be expectations of different inputs and different outputs. The example I give is training a model so that it recognizes, does the user want a whole page on everything that could ever happen in this disease? Or does it just need an answer here and now? Those are both very valid use cases, right? Like, I have 30 other patients. I don't want to read the whole thing about every single trial that's been done on this disease. And I just need an answer, yes or no.
A good example is having our tool work with calculators, this various medical calculators. This is something that was a relatively recent feature that we put in where if you want to compute a medical score, you can put that in. We've trained our model to recognize that. and bring up an interface for it. As Travis is saying, this is a really cool way to make sure that we have a very simple and easy to use interface. You don't have to find the right page where you're going to ask that question, but you end up getting hopefully the answer that you want, or whatever the situation is.
Yeah, in my anecdotal usage of it, I found it to be super helpful. Depending on how you tailor your input, you can get a guideline-based response or an EBM response, an aggregation of, the most recent evidence or randomized controlled trials, which I love. I mean, that's kind of both have significant utility, either from the teaching side in a residency training program or from just a, day-to-day clinical, sort of seeing patients. So,
I mean, there was a huge effort, multiple months to put all this together so that we could hit multiple different use cases. If you ask for patient-facing language and make sure it stays at 8th grade literacy level and accessible or the right language. If you ask for, a prior auth, that gives you the prior auth, that gives you the evidence for that indication. So you can fight the insurance company with the evidence in hand. The use cases are expanding. The hope is that we can continue to use just natural language so that there's not a bunch of button clicks to get it done.
And
that's great.
So far, so good. And I think just to kind of maybe pivot, make it a little bit more open to everyone, I'm curious, and you can't say OpenEvidence here, what AI tools or applications are you using that you find particularly valuable?
Yes, so I'm a big fan of the various coding related ones. I think as with medicine, you can't necessarily just take exactly what you get and just completely, whatever, ask it anything and get anything out. I think that you have to really learn how to use these tools well. And I think that having some expertise does help you interpret those results and make sure that you're doing the right thing for your situation. I find these are especially helpful if, let's say, you're writing code in some language that you haven't really spent much time with, or some framework and tool set that you're not too familiar with. These are really good ways to get a starting point or some base knowledge that you can build off of. I think that has a lot of parallels with what we're talking about, how if there's some condition that comes up that's something you haven't seen really often, it's a good way to refresh your memory or give you a starting point. For working in programming, I found that these really accelerate my ability to get work done in new domains or things that I haven't touched too much before.
Is there a specific application? So outside of the large language models themselves, are you using a Google Notebook, Notebook Studio, or any of these other learning type thing?
I think Copilot, which is built into VS Code, is something that I use quite a bit for auto completing, but also using ChatGPT or Claude just to ask questions more generally about stuff or getting help interpreting errors and such that come up. I think that they're all really helpful in that regard. I think those are probably the ones I use the most.
Yeah, I think I'm too old to actually use the Copilot. I use Claude and GPT to code for me all the time. For those people listening who are not coders, now's the time to learn. When was not to learn was when I learned it. 15 years ago, when you basically had to sit next to someone who knew what they were doing or spend 2 hours per bug on Google trying to figure it out. So if you use active learning and you're hesitant about learning code, now's the right time, because it is actually such a pleasure to code now compared to what it used to be.
It's amazing.
So I've tried Notebook. I can't say I've loved it yet. I do think at some point that way of learning and synthesizing will make us all so used to getting information so quickly that ADHD will be just a way of life. No one will have to process anything more than a TikTok, but I haven't picked it up yet.
That's amazing. I feel like the coding thing is just a huge breakthrough for people in research. The first time I tried to read in a file on SAS took me 2 hours to figure out how to do that. That was 6 or 7 years ago. I think we're getting towards the end of our conversation. We wanted to talk a little bit about the future of AI in medicine and maybe a broader question. I'll start with Varun. What excites you the most about the future of AI in medicine and what's maybe coming down the pipeline? It's sort of asking you to use a crystal ball, but what excites you about this field and how it intersects with medicine?
I think obviously with OpenEvidence, we're working a lot about textual data, right? But I think that as we get better at building these models that can just process crazy amounts of data, I think one thing that's going to be really exciting to see is how they actually make an impact on drug discovery or more basic science research. If you can make models that can, for example, process proteomic data, metabolomic data, biochemical data, and do that in a really accurate and scalable way, then I think that these could really accelerate the development of new treatments and with the field of biomedical research. And I think that using these models in language is such a cool use case and very easy one for us to understand because it's very easy for us to evaluate how well these things are doing. Like you can talk to ChatGPT, you can say, does this feel like I'm talking to something that knows what it's doing? And I think that is why this is the place where all these begin. But at the end of the day, what these models are really good at is just taking a lot of data and doing cool things with it. Hopefully, what we're going to see as time goes on, and these get more advanced, is using this type of technology to solve problems all across the world of science, especially in biology and medicine.
Oh, that's amazing.
I'll pivot a little bit what I'm interested in. I think there are two really big potential implementations that could transform how we practice in the next 5 years that I'm really excited about. One is real world evidence as an informing individual practice. To frame the first, what is interesting and frustrating to me is thinking about how we're trained as clinicians. This was actually something that came up before we started the show, but when it came to training, I'm one of the most fortunate people in terms of who I got to practice with. I learned how to treat pancreas cancer from the two world experts. But even in that setting, like there's so much variability in how one might practice and what is the right way to practice. And in the end, I learned from two people. And I don't have any idea the variation in how that works, right? And that's not uncommon, especially the more specialized you get, right? If you're in internal medicine and you end up going in cardiology, you probably work with a few attendings. Those 3 attendings may have all been trained by the same one person back in the day, right? Because we all are at the same institution. Using models and large scale data to better understand how is medicine practiced across a wider scale so that I can understand what are the variations in practice and what is acceptable, what are people doing? That's a descriptive analysis. And then a predictive analysis is, okay, what is the right way to do it? Now that pair that with outcomes, and both are equally important. I think a descriptive model to understand what the variations of practice are, what are the different ways people do things, would be eye-opening and illuminating and helpful to a lot of clinicians. So basically we can increase our sample size to understand how people being treated. So that's one. And that's going beyond evidence-based medicine. We can't run a randomized clinical trial on every single variation for every single person, right? But we can collect that information and then understand what people do in different situations. The other one is, how can we actually apply evidence-based medicine across entire populations to find people that fall through the cracks and do that in a really systematic and accurate way? So that is taking something that OpenEvidence is doing, but instead of just saying, this is the evidence, then applying it to the entire network of patients in real time. And then saying, look, this person, it's nobody's fault, but they haven't seen anyone for 3 months and the guidelines for diabetes have changed. Somebody should see that person and give them the new drug or whatever happens to be, right? That's the population health level. It sounds a little bit big brother in terms of somebody watching what you do as a clinician, but if we're being humble about it, we should all want it, right? We should all want some sort of backup system, help us make sure that we're doing the best for our patients. Those are two kind of very big aspirational things. I'm not saying that it's rolling out in your clinic in the next month, but aspirationally, those are two big picture things of how I see AI transform.
I actually had a little bit more I wanted to add as well, kind of more clinical and health focused. I think that through tools like OpenEvidence, but also things like AI scribes, we're seeing a lot of really cool instances where AI is becoming a really useful tool for one piece of the clinical workflow in the clinical life. And the thing is, if there's anything I've heard from people I know who are doctors, is that there's so much non-practicing medical work that ends up getting put onto your plate that makes it so hard to do the things that you like doing best and that you're trained for best, right? I think that one of the really cool future outcomes that could come from AI is that the more we create tools that are good at doing annoying rote work, and the more we can connect these together to form a streamlined process, the hope is these will free up doctors to do more of what they're good at. Because to be honest, it's a lot easier to make something that can answer specific questions or can transcribe spoken words than it is to make something that can do the intuition that doctors and clinicians use every day. And so our hope is that way before we'd ever be able to replace a doctor, we can make doctors' lives as best as possible to do what they like doing and they're trained for best.
And we do. Yeah, that was perfectly said. Go ahead.
I like Varun's answer better. Take that
one. No, I mean, that's like the central tenet of informatics, though, right? We're going to say that system plus man is going to be better than either by themselves. And I think you guys just laid out a great case for it. I think we should just let it go right there.
Yeah, I think that's a really good spot to end. DJ and I just want to thank you both so much for your time. I know you're both super busy, and it's a privilege to hear about OpenEvidence and your perspective on the field. Thank you again for joining us.
I appreciate it.
Yeah, thank you for having us on.
Thanks so much for listening to episode 10 of the Stat AI podcast. If you get a chance, check us out on X and Instagram and our newly updated website, stataipodcast.com. And make sure to tune in next month for some more amazing content. Thanks so much and take care.
Please note that the views, opinions, and information expressed in this podcast are solely those of the individual speakers and do not necessarily represent those of their employers, our sponsors, or any affiliated organizations. The content provided is for informational and educational purposes and is not intended as medical advice. We encourage you to consult with qualified healthcare professionals for any medical concerns or treatment decisions. This podcast is not a substitute for professional medical advice, diagnosis, or treatment. Listener discretion is advised.